So, welcome to the Tornado Cat Podcast Circle. We have a great audience over here, so let's go. All right. So quick agenda. Oh, speak over here. All right. We're gonna wait for 1 more minute. Oh yeah, let's go. Hello. How are you doing? So we have a wonderful audience over here.
Is this even better now?
All right, okay. We've doubled the number of people here. All right. Okay, let's get started. So Tornado Cash, hopefully you all have heard about it. Today we're going to start like deep dive into it. So I guess how familiar are you all with Tornado Cash? Have you heard of it? You know?
Wait, is this a thing called a mixer?
Yeah.
Okay.
So we're going to talk about mixers. So Tornado Cash is a mixer, and specifically it's a non-custodial mixer, but we'll talk about that. Yeah. So Tornado Cash, it's pretty popular, been in the news. It's kind of illegal right now, but we'll move on. Yeah. So quick overview. We'll start off by just talk about what Tornado Cash is. We'll move on into talk about mixers more generally, and sort of like what makes Tornado Cash different from your regular mixers. Then we'll move on to talk about ZK, and we'll talk about Snox, which is sort of what makes Tornado Cash different, and it allows the whole like non-custodial part of it. We'll move into the technical, which is kind of like a deep dive on the white paper. So I don't know if you'll pull up the white paper, but I have some slides on that. And then we have like a slide on, just regulations and what comes next. All right. What is Tornado Cash? So typically how transactions work on Ethereum or, most account-based cryptocurrencies is that if you have two accounts, let's say that, you have a person called Alice, and Alice wants to transfer 10 ETH from an account from her first account to a second account, then this transaction is publicly viewable by anyone on the network, right? So you can just pull up Etherscan and you can look at the transaction. Or you can look up Alice's wallet. So you can look up Alice 1 and Alice 2, and you can see that Alice 1 has sent 10 ETH to Alice 2. However, this is not ideal because sometimes you don't want people to know about certain transactions, right? So sort of like the guiding example that I use is that if you're, let's say, like a crypto hedge fund, right? You don't want other hedge funds to know the kind of positions you're taking. So you do value that kind of like, obscurity, I guess. And Tornado Cash is essentially an attempt to resolve this problem. So they describe it as a non-custodial platform for private transactions. And what that means is, as you were saying, Tommy, it enables a user to mix their ERC20 tokens with other users' tokens and retrieve them on the other side. So what does it look like? So if we go to like the previous example, we could say that Alice would put this 10 ETH into Tornado Cash, and that would be one transaction. So if we were to view Alice 1's account on Etherscan, we would just see that Alice 1 sends 10 ETH to Tornado Cash, and then Alice would log in to a different account, so Alice 2, and the second transaction would just be Tornado Cash to Alice 2. So what you're doing is essentially you're severing the link between Alice 1 and Alice 2. So people can move transactions between their own accounts or transfer to other accounts more privately. Hey Maria, feel free to put in any questions in the chat on Zoom as well. Just unmute. Hopefully the video's on. Cool. So yeah, essentially the point of Tornado Cash is that you cannot link an address with a transaction. And this is different from typical transactions, right? Because as we saw before, typical transactions, it's from address A to address B. Cool. Yeah, just quickly as to why it's interesting. Well, it's sort of like the best attempt that we, well, I guess had for on-chain privacy. Because again, if you're a fund manager, you might want to keep your position in crypto secret from other funds. If you are, if you're like in a country where it's illegal to transact with certain types of protocols or certain types of other people, then you probably don't want your government knowing that. And so on. So that's why it's sort of like interesting to see why Tornado Cash came into being and how exactly it evolved and why it's been a subject of regulatory concern and why it's been banned right now. And it's also interesting because the whole Bitcoin vision, like the one that's Doshi laid out, with sort of like a publicly viewable ledger of transactions. So it's interesting to see that the needs of the community have evolved to sort of like desire this privacy platform in which you can sort of like choose to obscure certain types of transactions. So it's interesting to discuss, even on a philosophical note, whether this is actually antithetical to the whole vision of, a publicly viewable ledger and to what extent, should a blockchain be public versus private. So it's a little interesting philosophical discussion, especially around the time when, it got sanctioned. That's when a lot of people sort of underscored the need for privacy, even in this public ledger. So it's a means of preserving that. And the second one is one of the best on-chain use cases for zero knowledge. So ZK, it's a very new and exciting cryptographic primitive that is slowly being onboarded to a lot of on-chain applications. And Tornado Cash is probably one of the application of ZK. And it just sets a template for privacy preserving applications. And yeah, like illegal stuff, controversy, that kind of vibes. It's always interesting to like look at those. Cool. Any questions on any of those?
I have a question. Okay, so if I guess like separate line between transaction between two wallets, like is it maybe like I'm kind of use this like
Yeah.
if you just look at like what wallet one sent out and then like the amount that wallet two received, would it kind of obvious?
Really, because it's like think of it this way, right? Right now, okay, I guess I should have named it better, but essentially what happens is I'm just trying to like color around the side. So you have like so previously on like Ethereum, right? It'd be something like so you go on Etherscan and you have like Alice 1, the Alice 2. And this is like pure right? But now what you do is you essentially split this into two separate transactions. So you have Alice 1, the Tornado, and Tornado Alice 2, right? And thing is, you don't know that Alice owns both Alice 1 and Alice 2 because on Etherscan, this would be like, something like random address, right? So it's like ABCD, this would be like 0x1234, right? How do you know that Alice owns both these addresses? Okay. So there is no way to like, connect this address ABCD to this address 1234. And especially if your point is relevant because if this is the only transaction that was happening on Tornado, then yes, you can connect, right? Okay. But if there are like, hundreds of other transactions on Tornado, maybe like, you have like 1, 3, 2, 4 sending somebody to Tornado, and you have like someone else withdrawing it. Then how do you know that, this account is like this and not this, right? So that's, the whole like privacy. Yeah.
Well, how does Tornado know like which account can retrieve them?
We'll get to that. So that's, that's where the ZK part comes in. It's essentially to do with like hashing, but we'll talk about that in very detail. But good question. Sweet. So those are good questions. Let's move on to talking about mixes a little bit. All right. So what are mixes? So mixes allow you to, mix your crypto, other users' crypto. And it also allows you to sort of like get it back from the other side. And these are useful in case you want to like, have a link between two of your accounts or your account and someone else's account. However, most cryptocurrency mixers, so like pre-Tornado Cash, were custodial. So if you've heard of like Blender.io, that is a custodial cryptocurrency mixture. And what that means is that they have access to your funds in the meantime. So sort of like, so like Web2 analog would be a bank, right? So the only guarantee that your bank gives to you is that when you ask for your money, they'll give it to you back. And in the meantime, they can do whatever. They can like give it out as loans, they can make investments. Your money the bank can choose to use the money that you deposited any way they like, right? But in the case of Tornado Cash, it is non-custodial. And at no point does the contract, like the Tornado Cash contract, or the owner of the Tornado contract have access to use funds. And how we achieve this is using ZK. So this is like, so let's illustrate this again. I like making diagrams. So let's say that the difference between, custodial and non-custodial mixes, it's not like, let's say similar premise, we have Alice who's trying to transfer money between two accounts. Let's say that Alice is trying to transfer money from her account to Bob's, right? So let's say that she has $1,000 in cash. So sort of like the traditional way that you do it is that Alice would go to a bank, and the bank would sort of give her a private deposit box, right? And give her a key to that. So the bank would give her a key to the deposit box. And Alice would put the money inside the deposit box, and then she gives the key to Bob. And once Bob has the key to the deposit box, he can walk in the bank and open that at any time. But during this whole time, the bank has the $1,000 in the deposit box, right? So they can just go in and use that. They can unlock it using the master key and get $1,000. So that's an example of a custodial mixer. In that, sure, you're still severing the link between Alice and Bob because no one knows that Alice gave the key to Bob. That can be done in secret. However, the bank still has access to the money. Now, what a non-custodial mixer would look like is, let's say that instead of directly transferring or putting the money in the bank vault, let's say that Alice just put some money in the ground, right? So she takes it out under a tree somewhere, and then she makes a treasure map that only Bob can understand. So maybe, it relies on Bob's birthday or some shit like that. So Alice makes a treasure map. So in this case, what's inside the bank is actual money. But now let's say that Alice, the first thing that she does is hides money, and she deposits the map into the bank. And keep in mind that only Bob can understand the map. Only Bob can understand the map, right? So the same thing happens. Bank gives the key back to Alice. Alice gives the key to Bob. And Bob can go into a bank and access this map at any time. And if Bob accesses the map, then Bob knows that, oh yeah, I know where the money is, so I can go and get it. However, this is non-custodial because at any point in time, the bank doesn't have access to the money. It only has access to the map. And the bank cannot understand the map, right? Because only Bob can understand the map. So in this case, even though the bank has access to the map, which leads to the money, it can't actually access the money. So it can't do anything with it. And that's sort of the analogy for, Tornado Cash. Is that technically, all the transactions and the money is stored in a contract that belongs to Tornado Cash, but the owners of Tornado Cash and the contract itself cannot actually do anything with the money. Only a user who has a key and who can read the map is allowed to withdraw it. So that's sort of the difference between that. And this would be something like Blender. And this is Tornado.
So who would use Blender?
So Blender is sort of the pre-Tornado protocol.
Yeah,
if you don't really care that the bank can use $1,000 and you use Blender, Tornado just enforces stronger privacy protection.
Has it ever been abused?
Sorry?
Has it ever been abused like Blender?
To my knowledge, not really, because again, the person creating this never chose to invest all these funds. At least it has happened with Blender. I'm not aware if it's been abused for other custodial services, but I'm not aware if anybody wants abusing it. But it's stronger privacy guarantee, and that's the possibility of eliminating abuse is why wait for it to happen. Yeah, so that's pretty much difference. And for those people on Zoom, I don't know if y'all can see this, but it's a little darker that made. But essentially, yeah, the difference is Tornado Cash that doesn't have access to your money. All right, cool. All right, moving on. Okay, so any questions on anything else that we covered? People on Zoom?
Was the use case for Blender also just so that you could like settle the
Pretty much, yeah. It's similar sort of use case that, both of those allow you to deposit money as one account and withdraw the same money as another account. So, yeah, and actually, I should have qualified that well because since Blender is custodial, like let's say you deposit like, 5 each, right? When you withdraw from Blender, it may not be those actual same tokens that you deposit. You'll still get 5 back, but it could be like, 5 that someone else deposited.
Right.
However, in something like Tornado, you will guaranteed get back the 5 that you deposited. So that's another distinction between the two.
Is that an important thing? Does that change anything?
Really, just difference in implementation. Cool. All right, let's talk a bit about ZK and Snox in specific. So again, we're not going to go super deep into this. I know like Emma is doing the whole like ZK learning group, so go talk to her if you're interested in that. But we'll just go over like some primitives and just, quick couple of slides just so we understand, sort of like at a high level what Tornado is doing, because this is sort of how it maintains the non-custodial aspect of things and how it sort of like enforces protections on withdrawals. And it's pretty interesting. So what's a ZK SNOC? So a SNOC stands for a succinct, non-interactive argument of knowledge. And what it is that it's a cryptographic proof. And essentially, it aims to show a verifier that is, a particular person that another person called a prover knows a certain piece of information, but doesn't tell the verifier what that information is. So concretely, for example, like on a night out when you're hitting kips, you want the bouncer to know that you're 21, but you don't want him to know your birthday, right? So in that, something you might want to do is that there's this new law that Californian licenses for under 21, for people under 21, are vertical instead of horizontal. So if you go to KIPS and show the bouncer that you have a horizontal license and you cover the date, then the bouncer knows you're 21, but he doesn't know like, your actual birthday. So you manage to show the bouncer that, oh yeah, like you are 21. However, he doesn't get to know your actual birthday. So you still manage to hide that piece of information from him. And extending this analogy in Tornado Cash, well, it's a very huge extension, but anyway. In Tornado Cash, so in this case, the KIPS case, the prover is you. So you want to prove to the bouncer that you're like, at least 21. And the verifier is the bouncer, because the bouncer looks at the ID, is like, oh yeah, it's horizontal, you're all good. Because I know that, you have to be at least 21 to get that. Okay, so in Tornado Cash, the prover is the account that's withdrawing funds. And essentially the way that it works, and we'll get super into depth in this, is that they want to show that they know, this, it's a secret value essentially. And that secret value, you can think of it as kind of like a deposit slip, right? So if you go up to like a bank, you want to show that, oh yeah, I deposited this money and now I want it back. So I give like a deposit slip or kind of like a deposit proof, right? And I don't want to broadcast that information publicly, because if I broadcast my deposit proof publicly, then anyone can go up to a bank and like claim my funds, right? And I don't want that. And the verifier in this case is the Tornado Cash contract. And actually Tornado Cash has a set of contracts. So, I think there are like 3 main ones. One handles, the like sending and receiving tokens, one handles storage, and the other one handles this verification. So it's one of the Tornado Cash contracts. And essentially checks your proof. And if the proof is legit, then it releases the funds to, the withdrawing account. And yeah, just a couple of implementational details. The specific sort of like SNOC generation algorithm that Tornado Cash uses is called Grot16. And again, this is, so like a bunch of complicated math. So we won't be going super into technical details. But honestly, since it's like a small group, I could probably do a little bit about like another ZK protocol, like FDR, if y'all want to like go into that. Okay, cool. But yeah, so if you want to learn more about this, then go to the ZK learning group. I think they're like gonna actually cover like Grot16 and everything, so that's pretty cool. But yeah, I think we could do like, what's the time? Okay, it's like 12:40. I think we have some time. So let's just try to cover, a little bit of ZK stuff. I'm just gonna like erase this, but we need this in a moment. Yes, essentially, what a ZK proof is, the way that typically works out is by using polynomials. We can wait for get back.
Did you eat lunch?
Yeah, I got here. I'm not trying, bro. Is that better?
Yeah.
It looks bad, bro. Okay. It's like 12. How long is it supposed to be for? I think it's like 1:30. Oops. Bro, Lawson just texted me back. And after it's gonna pull up. Like, probably not.
It's a rainy day.
Yeah. How y'all doing on Zoom? Well, also, I never checked, but y'all can hear me and shit, right? I'm guessing it's yes.
What are we doing?
I think it's like Albert and Maria right now. I don't know if there's anything else. Yeah. Alright. So essentially, the most common way to sort of like create CK proofs is to use polynomials. And essentially what a polynomial is let's call it P of x. It's like some function of x, right? So in this case, it could be something like, oh yeah, 1 plus 3x plus 4x squared plus 2x cubed plus 7x4, right? So this is a polynomial. And let's say that this sort of like encodes my message or my secret or whatever. So essentially what you want to do is you have the prover and you have a verifier. And the prover knows P of x. The verifier does not know P of x. And the prover wants to tell the verifier that, okay, yeah, I know the value of P of x. So I guess once to show they know P of x. And the verifier, they don't know P, but they can always like, put a value of x, and then P would just sort of be a black box and spit out an output, right? So in this case,
They
they
want
can,
access to people.
yeah, so they don't want access to P, they want to verify that the prover knows P of x.
But like he has like the verifier has access to
Yeah.
people.
Yeah, exactly. So verifier has access to P, and they can just like, they can do shit like, oh yeah, P of 1 is like 1 plus 3 plus 4 plus 2 plus 7. What the hell that is? It's like 17. They can do shit like that, right? So they can verify that, whatever the prover says is correct. But they don't know this exact like formula. Because, if P of 1 is 17, then P could be something like 17x. It could just be 17. It could be that. It could be like a bunch of stuff, right? So they don't know what it is. So essentially the problem now becomes, how do I sort of like reduce this and communicate it to the verifier such that, the verifier cannot know P of x, but the prover, but they can know that, oh yeah, the prover knows P of x. And the way the FDR works, and it's been like a year since I read Matrix Grok, so this may be incorrect, but essentially what you do is that you come up with like, if you're the prover, you come up with like 2 new polynomials. So you come up with Q of x, which is all of the even terms, even power terms in this case. So it'll be 1 plus 4x squared plus 7x4. And you come up with R of x, which is the odd number terms in that. So this would be 3x plus 2x cubed, and so on. So in this, you can also represent this if you were to shift your variables. If you have Q of y, then you have 1 plus 4y plus 7y squared. If you have y is equal to x squared, right? And similar thing over here, you can just eliminate the x and have something like this. Oh, let's do it. Let's keep it as is. So essentially you know that P of x is equal to Q plus R of x. And if you were to like remove the x's from here, you could do something like Q of x plus x times R of the x. So now you have 2 sort of like even part polynomials. And you can sort of like decompose P of x into this. And if you're all like familiar with the fast Fourier transform, it's like similar sort of deal that we're doing over here. So now, what the prover does to the verifier is they send a verifier a bunch of sample points. So verifier will send the prover a bunch of sample points, right? So they'd be like, oh yeah, just like do 1, do 2. Oh, let's do -1. It'll be easier. So 1 minus 1 0, right? And essentially, the prover knows the answer for all of these. So P of 1 is 17, P of -1 would be -3, or what are you gonna say? Let's do -2, 0. It's like -7 or something, right? Well, +7, whatever. And P of 0 is 1. So they know all these values. And essentially, what the prover would do is that they would compute these values for Q. So they'd compute Q of 1, R of 1, Q of -1, and R of -1. So Q of 1, so let's just take the 1 case, right? So Q of 1 would be 1 plus 4 plus 7, that would be equal to, what is it? What kind of math? 12. R of 1 is 3 plus 2, that's 5. And they will return these values of Q of 1 and R of 1. And now the prover knows that P is equal to Q plus X RX. So this is something that the prover can communicate to the verifier. And they will just plug in the values that, the prover gives them. So the verifier would say that, okay, the value I've got for Q of 1 is 12, plus 1 times 5, that's 17. And that checks out with what I know. And it turns out that, statistically, if you do it with enough random points, and if you sort of like go decompose this even further, then you can prove it like, a certain amount of probability. So you can sort of like be arbitrarily specific, but, like 99% probability or whatever, that the prover knows P of X. Or else they wouldn't be able to give you these values that consistently validate the P of X. So that's essentially how like something like FDI works. And again, this is not like still fairly high level, but it's like something bare ones over here.
Wait, it's called FTI.
Yeah, this is sort of like one of the main or first ZK protocols.
Wait, so does the prover know PFX? Like they know what PFX is? Or do they know?
No, they don't know that. They don't know the actual like expression for PFX, but they can evaluate it at any point.
How about the prover?
The prover knows PFX. So that's why they can do this decomposition, right?
Well, wait, why can't they just like plug in the values without PFX?
Sorry, what's that?
Why can't they just like plug in the values that are given?
Like over here?
Yeah.
Well, then how do you know that the prover knows P of X? Because it could be something like, if P of X was 17x, right? Then so essentially, the verifier wants to know. Wait. Yeah, can you just like rephrase the question?
Yeah, that's right. Yeah. So you're saying that the verifier sends a bunch of sample points to P of X.
Sure.
And P of X, or sorry, the prover, yeah. When the prover basically finds out, or like they plug in the values, the decompose function and find like the corresponding value. And if the corresponding value matches with what the verifier has, over a certain amount of times, then like it's statistically probable that we know what P of X is.
Yeah, but it's not like the only way you know that is by these decompositions, right? Because if the prover could not decompose it, or to decompose it and gave you the wrong answers, then the verifier immediately knows that, oh yeah, they probably don't know the effects. Because, for example, if the prover thought that it was 17x instead of that, then if they were to compute these polynomials, they would give, a completely different answer. Right. So essentially, the way that you can take it is that for the verifier, P of X is sort of like a black box, right? Yeah. And you can always verify that, if you put 1 into the black box, you'll get 17 out. And you want to know that the prover lives inside this black box and knows what the effects is. So if the prover did not know that, then it's like immediately obvious that, because I can just pass, a bunch of sample values, and if they give me like one wrong output, then they probably have a different function.
Yeah. So
that's the one that, I'm trying to guess.
Yeah. So I guess my question is then, like, if that's the case, then if prover knows P of X, then why is the decomposition necessary? Can't they just plug in the values into P of X and that they would still get the right answers?
Well, it's because the verifier doesn't know PFX.
Right, the prover, Yeah, the prover can do that at any time, but the prover wants to show the verifier that they know prefix.
Okay.
Like anyone could plug in the values and just say that, oh yeah, I get 1731. That's like public information, right? But that doesn't say that, oh yeah, I know what the effects is.
Okay.
It just means that I have access to, this whole system.
Okay.
Yeah.
For the verifier, could you just like plug in enough points and you could find POS?
Sure, but that's computationally very difficult, right?
Oh,
Because,
is
okay,
it usually like?
this is,
very hard?
yeah, it is pretty hard, especially in practice, you kind of work in like prime fields.
Oh, okay.
So that just, so like, in this case, sure, you could probably guess it if you take like enough guesses, but in the prime field, this whole thing could be squared and end up in the same thing. This whole thing could be like, the power 12.
Yeah.
And if it's like mod 12 or something like that, again, I forget about what I'm at, but it'll result in the same thing. So that just makes it like computationally infeasible. Yeah, that's a like high level overview. And Grok 16, this makes it a bit more computationally efficient. Because it turns out in practice, you don't need to do all of this computational work. There are some like tricks to communicate the same sort of like message. And that's sort of like what Grok 16 does, but base high level overview. Cool. And the way that this is actually implemented in code is that snarks are generated by arithmetic circuits. So this is sort of like, if you ever take like 16B, you can have like electrical circuits, right? So this is similar vibe, but you can sort of like define mathematical operations, and it just shows you that, okay, if I have, a particular input and a particular output, it just says that, it just sort of like construct these processes, like decomposing polynomials, sending those values and verification and things like that. And these are written in Circom. So this is sort of like general purpose language for arithmetic circuits. And these Circom circuits have the property that the output, which is the sort of like validity proof, it does not contain any information about the inputs. And that is called, perfect zero knowledge. Is that, if I look at the output, then I can't guess what the inputs are, which is like kind of important, right? Because if you could, then, if your input is like a bunch of secrets containing like, your password, then you're kind of fucked. Fuck my French. And yeah, aside from the fact that, if it's valid or not, like someone needs to be able to compute if it's valid or not, but apart from that, there's like no information. And these circuits, so these Circom circuits, they run on the user's front end. So these are never, run on like the smart contract or on chain. So all of the secret values are kept locally. So there's a local inputs in the user's browser, and these are never transmitted. So the secret values that you have as inputs to the snark circuit remain secret because they only ever execute on the user's local environment. All right, that was a lot. So any questions?
So like an example, but would, at least I know Grok 16 is different. Yeah. In this example, would be like P of 1 to 17.
Yeah, so in this case, it'll be the input would be like something like this actual polynomial.
Oh, the actual polynomial.
Yeah,
oh, okay.
so it's like 1 plus 3x plus 4.
Oh.
Yeah, and we'll go to like, how Tornado does it and the specific inputs for that as well. Cool. Any more questions before we move on to actually talk about Tornado? Okay, cool. Let's start with some technical specifications for Tornado Cash. So let's talk about pools first. So the way that Tornado Cash works is that you have pools where users can deposit and withdraw a set amount of tokens. So you could have like, a 1 ETH pool, a 0.1 wrap BTC pool, a 100 DAI pool, and so on. There are like a bunch of these, or there were a bunch of these. And, it's applicable across a wide variety of ERC20 tokens. So again, this is like based on Ethereum. So it's supposed like all ERC20. And the question is, why not allow sort of like arbitrary amounts, right? Why do you only want users to like sort of like deposit and withdraw 1 ETH at a time or like 100 ETH at a time and not like, 1.1 ETH and so on? And essentially the reason for that is safety in numbers, because let's say that, yeah. Oh, is it? Oops. Yes. Anyhow, I'll just brace this. Like, y'all don't need to see. It's like, sure, they can, but anyone wants to see it before those. I'll just use this shot. I think that's But yeah, exactly what happens here is, let's say you have like 3 people, right? Let's say you have Alice, Bob, and Carol, right? And all 3 of them interact with the Tornado Cash contract. And let's say that Alice sends 1 each, Bob sends 1 each, but Carol sends 100 each. Or just any arbitrary amount, right? And on the other side, you have withdrawals. So you have XYZ, you have 1, 2, 3, and ABC, right? So you have 3 like unknown addresses, and you don't know who to. So XYZ withdraws 1 each, 1 to 3 withdraws 100 each, and ABC withdraws 1 each. Then you can immediately find out that, oh yeah, Carol is 1 to 3. And this sort of works for like, any arbitrary amount. So it's like 1.23, then, you sort of like immediately make the link between the accounts. So it's just sort of like, what's the whole point of using Tornado in that case? And this is how it worked for the longest time in Tornado Cash Classic. But in sort of like a new update, Tornado Cash Nova, they sort of like allowed for arbitrary amounts. So you could probably have like, 1.2, 1.1, whatever. And just because of like the sheer volume of transactions in and around this particular amount, it was like kind of hard for people to know, what exactly these addresses are.
It's too low.
Yeah, exactly. The variance is too low, and then you have shit like gas and everything, you use layers, so it's hard to like figure out the exact matching. However, if you use like an amount that's vastly different from like like me, maybe if you have like 5.6 each, and then you could draw 5.6 each over here, then it's pretty obvious that Carol is 1 to 3 again. So that's sort of like why that's the main motivation for introducing pools in Tornado. Yeah.
If you have pools, and let's say if the pool is 100, like let's say you have a pool of 1 ETH,
Yeah.
and you want to send like 50 ETH.
Yeah.
You just have like 51 ETH transactions.
Yeah.
And then on the other side, they would also have 51 ETH withdrawals from
Yeah.
one account. So wouldn't that your fund?
Yeah, it's not your fault, but it's just more computational work.
But like they would still like if there's only 1 ETH
Yeah.
pool, like how does that hide it? Because this I send 51 ETH
Well,
transactions.
Yeah, but the thing is there are hundreds of other transactions happening in the same one pool, right? So your 50 transactions aren't the only things that happen. So in this case, maybe this is actually 50 transactions for 50. This is another 50 transactions for 50. This is another one. So it basically reduces the same problem. Like how do you distinguish between these? So it still maintains, the same level of security. But yeah, that goes to show it's basically safety in numbers, right? Because if you only have 1 transaction going on, or if you only have 2 transactions going on, it's like it's pretty trivial to figure out, at least in the 1 transaction case that this account is the same as this account. Okay, cool. All right, so that's about it for polls. Okay, let's talk about actually depositing funds. So the way it works is that there is the Tornado Cash contract for each specific pool. So each specific pool has like a contract on each mainnet. And let's assume throughout this entire example that they're calling the contract for the 1 each pool. And it works the same way for like any arbitrary amount. So what the user does is that they generate 2 random values on their end, so locally. So there's one secret, which will denote as R, and it's another value called a nullifier, which we denote as K. And what the user does is that they hash these 2 values to get a value C. And they use a particular hashing function called the Pedersen hash function. And essentially this is, it's more efficient for ZK because it's sort of like, it reduces the computational load of polynomial commitments. So shit like that, like a polynomial wrote at the other end, it just makes that process a little bit easier. And essentially what the C is used for is it's a deposit receipt while withdrawing. So the user of Tornado Cash will compute the C value and then they'll store it locally. They'll store the C because they'll need it whenever they want to withdraw their money. And then obviously they'll also store the secret and nullifier because these are like, again, things that they'll need to get their money back. And what the user then does is that they send the value of C, which is the hash, and the value of K, or rather the hash value of K, to the Tornado Cash contract. And the contract actually stores both the value of C and the hash value of K. And since the contract stores it on chain, both of these are visible to just anyone who accesses the contract. So both of these are publicly visible. They aren't sort of like private. And the one ETH that the user sent to the Tornado contract is dumped into another custodial contract. So essentially at this stage, what happens is, I'm just gonna say like user, let's say depositor, rather, depositor contract, and we'll get to that on withdraw. So now the depositor, they have R and K, the actual values, and they have C because it's just a hash of R and K, right? So they can compute this at any time. Now, the contract would have C, and it also have the hash of K. So this is what happens at deposit, and they'll have the one ETH that the depositor sent it, right? Okay, so this is what happens while depositing. And okay, let's talk about nullify. So over here, we generated two random values. So we generated sort of like a secret R and a nullifier K. Well, why do you need like a second secret value, right? Why can't you just generate like one random value? Because that could just be like, if you take the example of like a private key, right? That's just one random value. So why do you need to generate like another one? And the reason we do this is essentially to prevent double spend. Because if you generated just one random value R, then what a withdrawer could do is that if they knew R, they could just say that, okay, yeah, I know R. So I can compute the hash of R. This checks out. So give me back my money. So they get one each. And they only have one each now, so they're happy. However, there is nothing in the contract that prevents them from essentially repeating the process. So they will call HR again. And since this checks out of the contract, they will get one more. And this is, textbook double spend. So now to prevent that, what do you do? Or what Tornado Cash does is that it introduces a second random value. That is, it's called a nullifier. And it stores the hash of the nullifier. So same principle. If the withdrawer has R of H and K, then they'll need to compute, C prime, that's H1 of R and K. If C is equal to C prime, then you have one ETH that is transferred to the withdrawer. So now they have one ETH. And what you also do is that you compute the hash of K and send it to a contract. And if these two hashes match, then what happens is that the contract removes this from the list. So the second time that the withdrawer tries to call R of K, let's say they're attempting a double spend, you do the same thing. And the C's check out. Okay, fantastic. But now when you sort of like send the hash of K, you don't have a match because that has been removed from the list. So the transaction doesn't go through. So this is essentially, the nullifier is used to prevent double spend. And yeah, I mean, the slide basically goes over that. To recap on deposit, the nullifier, that is K, or well, I should say the hash of the nullifier is added to sort of like an on-chain list that is maintained by the contract. And on withdrawal, this hash value of the nullifier is removed from the list. So at every time during the withdrawal process, you check, or the contract checks that, okay, is the nullifier on the list? And if it's not, I cannot withdraw. If it is, then I can withdraw, but I also remove it from the list to prevent double spend. All right, any questions on any of that?
Why not use like a more like I guess why not just do like a hash map table? You have like C, like let's say you only have one hash, and you only have R.
Yeah.
Do like R to like some ETH amount.
Yeah, I'd say that the answer to that is just like computational efficiency, because like for example, hash maps are like terrible to store in in Solidity and like Ethereum. They take up like 8 of the storage space. And this way, what you're doing is the contract only ever stores the nullifiers or the transactions that haven't been withdrawn yet. And as soon as you withdraw a transaction, that's gone. You just delete that value because you can never call it again.
And then does it keep C in the contract?
Yeah, so we'll get to like how C is stored right now. So yeah, you have seeds in a mobile tree. Okay, that's actually a perfect segue. So Tornado Cash uses, it stores like a couple of things, right? Apart from like the user funds, it stores C and a hash of case. So the way it stores C is through a Merkle tree, and the way it stores hash of case is just a regular list. So specifically, okay, are you all familiar with like Merkle trees? Okay, sweet, we can run through this quick. So what a Merkle tree is, and there's like a little video over there, but I'm just gonna like roll out all the explanation right now because I feel like it. Yeah. So the Merkle tree is essentially a data structure, right? And what it is, let's say you start off with like an array of values. Right, so let's make it fair now. Let's say you have like 4 values, right? And let's just call these like, let's say all of these are like C0. I think that's what the video uses. Okay, you have this list of 4 values. How do you store it efficiently? Well, you can do these first 2 values and create a new value that's essentially the hash of these 2 values concatenated together, right? And you can do a similar thing for the third and fourth value. And I don't know, let's call it C1, right? So these are so like 2 nodes. And then at the top level, you can do the hash of these 2 values. So you can have C2 is equal to the hash of C1, concatenated with C1. And what this allows you to do is that if any of these root values are changed, so let's say that we change this like, I don't know, C3, right? Oh, let's just say X. So now the value immediately above it is changed because now it's no longer C0, it's X. And this whole thing is propagated upwards because now it's on C1 and C1 prime. And so C2 would also change. And this essentially, whenever you update any of the leaves in the Merkle tree, the change is propagated all the way up to the root of the Merkle tree. And that's useful for, just efficient storage because now you can only keep track of like the root header to verify that, oh yeah, C0 is in the tree. And also for Tampa evidence, because if you just randomly change its value, then it's immediately evident because you get an entirely new root. So that's just a quick primer on Merkle trees. And the way that Tornado Cash does it is that let's say that you're storing these C values. So for 4 different transactions, it might be C0, C1, C2, C3. And it's basically like textbook Merkle tree implementation. So at each level, you sort of like propagate these 2 transactions that are right below it. And it eventually goes up to a root. So the hashes are stored as Merkle trees, and this allows you to quickly verify if a transaction is actually inside tree, as well as storing it more efficiently. And it also has a large copy of Tampa evidence. So that's how the deposit hashes are stored. Yeah.
Wait, can you walk through if I had a new deposit and I have a new C hash, how would I now append that to this?
Sure. Sure. So at the start, Tornado Cash has some sort of like default values inside the leaves of this Merkle tree. So this value is, I think it's like the CAC hash of the string Tornado. So I think don't quote me on this, but I believe this is what it is. So this is like some sort of default value, right? So let's say you make a transaction and you come up with a hash value, like let's say C1, yeah? So now the first thing it does is that it looks into the last leaf of the Merkle tree, or the first available leaf. And it looks at it and says that, oh yeah, is this leaf available? Now it is, because right now it's set to a default value, right? So there's no transaction information there. So if it is, then it just slots in C1 at this value and moves the pointer to like the last or like the next available value to the next leaf. And then it just sort of like recomputes all the hashes all the way up to a tree, which is, not actually that bad because it takes like logarithmic time in the depth of the tree, which is not too bad because I don't remember the exact number, but it's not very large in terms of like the current number of transactions and stuff.
And so let's say like they want to verify if a transaction was in the Merkle tree,
Mhm.
they would. How would they do that?
So essentially what you do is that you would take all the neighbor transactions, right? So let's say that we had like a bunch of,
But that means you would have to store all the C transactions.
sorry?
That means you do have to store a list of all C transactions.
Right, you do have to store a list, but sort of like verifying. Yeah, you have to sort of like, again, it's been a while since I read up on Merkle trees, so I need to like look at that exactly. But yeah, you need to store all these hashes. These are already in storage. It's just that every time you need to prove that, let's say that you want to prove that C2 is in a tree, right? The way that you typically do it in regular list is that you go through all the values and you see, if C2 is there, which takes like, linear time. What you can do in a Merkle tree is that you can look at the neighboring values at each level of the tree. So in this case, you look at C1. You compute a hash and you have like this value. Then you look at this value because this will lead you to the next level. So what you do is that you only need to look at log n number of some like other transactions in order to verify that C2 is actually in the tree. So it's more computationally efficient. And in this case, it's a small array, so it doesn't really matter which way you do. But if you have like hundreds, like thousands of transactions, then it's a huge computational improvement. So yeah, it just sort of Merkle tree is more efficient for both lookup, storage, and so like tab averages as well. Cool. Let's speed up.
In this video,
It's fine. We don't need to watch that, but good resource. All right. Let's quickly talk about withdrawal funds. And this is all like this is the most interesting part because this is where like, the ZK stuff comes in. Okay. So let's clean this up a little bit. Also, let me tell them it's going. Hopefully people on Zoom can see what I'm doing. Okay. Can you all see it? So you have the depositor, you have the contract, and we have the withdrawal. Okay. And we know the depositor has R and K, a secret and a nullifier, and they can compute a hash, which is the partition hash of R and K. Oh, and another thing about Merkle trees in Tornado Cache, this hashing algorithm is not the same as a partition hash. It's called a MIMC hash. And this is, another common hash function. Again, it's just reasons for computational efficiency. But yeah, that's why I use H1 and H2, because H2 represents the Merkle tree hash. Anyhow, so you have the depositor, which computes the partition hash of R and K. The contract stores C and it stores the hash of K. And also has, the one ETH in custody. And now let's move on to the withdrawal, right? So the withdrawer needs to know R and K. That's, they need to know that in order to withdraw. That's what it's talking about. That's not like you can think of this as a private key, right? Well, how exactly do you communicate the fact that you know R and K to the contract without revealing R and K? Because if you were to reveal it on the network, then for example, it's easy for something like front you by looking at that and like sending that to a contract before you do, and then you're kind of screwed, right? So essentially what you do is that you use the sort of like SOCOM circuit that is in Tornado Cache repository to generate a snark proof. And how does that happen? Well, there is sort of like a withdraw.SOCOM circuit in the Tornado Cache contract. And what you do is that the withdrawer calls it using a certain set of inputs. So there are two different sorts of inputs. There are public inputs and private inputs. So the public inputs are, the Merkle root. So it's sort of like this root of, whichever tree the transaction belongs into. The nullifier hash, which is this. Again, this is public information. And the withdrawal address, right? So what address you want the funds to come to. And you also have private inputs. And private inputs are the secret nullifiers, so R and K, as well as the deposit slip C. And the reason that you have both public and private inputs is that note that all the snark generation happens locally. So the private inputs are things that they aren't ever broadcast out into the network. They only ever stay on your computer. However, the public inputs can be broadcast out in the network along with the validity proof, because it's stuff that the contract needs to know, for example, the withdrawal address, in order to know where to send the funds to. And it needs to know the Merkle root to figure out oh yeah, does the C actually lie in that particular tree? And it also needs a nullifier hash in order to prevent double spend, as we talked about. So this is why you have two different sets of inputs. And we're just gonna black box the snark generation for right now. But essentially the withdraw circuit generates a snark proof that this secret and nullifier correspond to this value of C. So essentially what the withdraw does is I'm just gonna say snark. And I'm gonna say RK implies C. So this is sort of a validity proof that's generated by the withdraw.circom circuit. And the withdraw sends the snark proof to the contract. Right? So again, by the properties of the snark proof, you aren't revealing what R and K are. This is again Groth 16, and the property of Groth 16, as with most snark proofs, is that they are pure zero, perfect zero knowledge. And that means that this actual output snark RK implies C. This does not reveal any information about R and K. So you send this snark proof to the contract along with your public inputs, your Merkle root, nullifier hash, and withdrawal address. And then what the contract does is that it verifies this proof. And this happens on chain, right? So whatever the contract does is on chain. And it can easily verify if this proof checks out or not, because if it checks out, then they can just see the value of C. And if it checks out, then yeah, great. So it verifies the snark proof on chain. And the other thing it does, and this is again to prevent double spend that we covered again, is that it verifies that so one of the public inputs is nullifier hash. So it verifies that these two, or it verifies that the nullifier hash actually exists on the list of nullifiers. And if it's not, then you can't withdraw. If it is, then you remove it. And once that is done, you just transfer the funds to the withdrawal account. So, okay, any questions about withdrawal? This is, kind of abstracted that away, because the actual process of how you generate a snark is, you probably need a better understanding of Groth 16 to do it. So we could probably go into that. There's a bunch of mathematical formula on the white paper. But I think we're kind of running low on time, so I do want to get through most things.
I guess I just have one question. Is the private input? I thought the deposit slip C was public, but it's stored on the chain. Why is that considered private?
That's a good question.
Is that just so it's locally run on the server?
Yeah, I think the deposit slip C is public, so it doesn't really need to be a private input. I'm actually not sure, because again, if R and K legit, then you can just recompute that, right? So. Yeah, I don't know, but I guess that's a way to define it. I'm not sure why it is. There might be a reason, but yeah, it is public information. So I think it just literally might be the case that the withdrawal needs that as some sort of input, and it just chose to make it private because why not? I guess. But yeah, that's a good question. So I can double check on that. Yeah, and another main point is that the snark generation process happens off chain. So these private inputs are actually never broadcast on chain, which is why they are private. Okay, cool. I think that's about it. Oh, relays. Yeah. So one last point is that in order to withdraw from Tornado, the withdrawal account must pay for the smart contract calls over here. So whenever you call it smart contracts, you need to pay gas, right? You need to pay ETH. However, if you were to transfer ETH from the depositor to the withdrawal contract, then you're creating a link. So what's the point if you're not using Tornado Cash if you're just going to link it anyway? And in order to avoid this, there are nodes called relays. And what a relay is that the withdrawers can choose to sort of essentially sign a message. So they generate this snark proof, and then instead of directly sending a contract, they send it to a relayer. They have the snark proof. And they have, a signed message from the withdrawer saying that, oh yeah, you can like sort of like withdraw this money from me. And once they have that, this relayer can sort of like call the contract. So they can sort of like front the gas to the contract. And same thing happens as a regular withdrawal. And you probably have like maybe like 0.99 each go to the actual withdrawal. And then the relayer takes a portion of the fees. So it's like 0.01 each. Goes to the relayer because the relayer paid for gas. So this is just, in this way, the withdrawer never actually needs to have any actual ether to call a contract. Because they can just go to the relayer will cover gas and it'll take a fee from, the actual funds that a contract sends to the withdrawal. And yeah, the relayer never actually knows the secrets. Because the relayer just has snark proof. And the snark, recall, doesn't tell you any information about RK.
Oh, because the snark, the withdrawer gives the relayer the withdrawal account, so the contract will directly send to the withdrawer.
Yeah, so the contract will directly send to withdrawal address because recall that, the withdrawal account is sort of like a public parameter.
So how does the relayer able to take because if the money is sent from contract directly to withdrawal, how's the relayer able to take it?
So there are a couple of optional fields in the sort of like withdrawal contract or Tornado Cash in which you can specify, relayer address and like a relayer fee. So the relayer just like fold that in, and in that way, the contract will send like in this case like 99% to the withdrawal and 1% to the relayer.
So the contract will feel.
Yeah, so in this case the fee would be like 1%. But yeah, in case if you're not using a relayer, then you just don't need to fill in those arguments. So in that case, 100% of the withdrawal money would go back to you.
But then that means the withdrawer needs to have some.
Yeah, they need to have ether to pay for gas. The point of using a relayer is that you don't need to pay for gas.
Is it popular to use relayers?
Pretty popular. So at least like Tornado Cash has like a whole relayer registry list. And the good thing about using a relayer is that you can literally just like create a new account and then just have it like, if you want to transfer an account from like, let's say a tainted account, you can just spin up a new account and just get that without having like transfer ether. So it works in that way. And it's pretty popular. Well, I guess it's not popular now because it's fucking banned, but it was pretty popular.
When was it banned?
2022. That's when the OFAC sanctions came in. Well, in the US, but functionally, like not many people use it now because regulation, which will we talk about. Yeah.
So could you explain again why, like the need for relayer and like why it would be that it was a link between us?
Sure. So let's say that you know that the withdrawer needs to call the contract of Tornado Cash, and in order to call the contract, you need gas. In order to pay for gas fees, you need ether in your account. How do you get that ether? Well, you either have to go through like a central provided on-ramp, in which case you're doing KYC, in which case what's the point of like this whole thing? Or you take it from an account, or you transfer ether from an account that you already own to the withdrawal. So if you transfer, let's say one like 0.1 ETH to pay for gas, right? Then what's the point of using Tornado? Because you just created a link by transferring ether. So in case you just want to like literally boot up a new account and just get your money without having to like, sort of like initialize any liquidity, then you can just use a relayer. And this will like circumvent the whole initially sending money for deposit part of it. Yeah.
This is just like a general on-ramping question, but is there any way to get money on chain through like centralized exchanges?
Any money you get on trade through centralized
Like,
exchanges?
it's the only way, let's say I have like $10 cash.
Right. It's the only way through centralized exchanges?
Yeah.
I mean, at least in the US, yeah, basically, because like it is pretty we'll talk about that. It's pretty regulated right now. So like the only way to like technically not get it through a central provider is like, oh shit, you have Bitcoin, I'll pay you $10 for it to send you. Like, it's someone who already has crypto sending you crypto. But the only way to like mint your crypto or like register for like new accounts and sort of like onboard liquidity onto them. At least the most common way in the US is through, your Coinbase is your Mars, whatever else, like MoonPay and stuff. Yeah, it's actually like a pretty big problem. The on-ramping thing, because again, I mean, it's literally the question of like how public / private do you want your blockchain to be, and like what level of government interference do you want? Do you want to do like KYC, AML? How so like antithetical is that to the vision of Bitcoin? Oh, it's something that people are figuring out right now. Okay, and I mean, just to finish off, like in 2022, I think it was like July, I don't remember the exact date, but whatever. The US Treasury, OFAC, that's the Office for Foreign Asset Control, they sanctioned a bunch of Tornado Cash contracts. And the reason for doing this was because a North Korean hack group that exploited, I don't know if you're all familiar with the Roland Bridge hack of Axie Infinity. So it's basically like, large cryptocurrency theft, like I don't know, $600 million, something like that. And they used Tornado Cash to sort of like essentially embezzle their money. And the OFAC essentially went on Tornado Cash and they're like, oh shit, like you're enabling illegal activity, so let's shut you down. Or at least like, bar US individuals and organizations from transacting with you. And because of that, most users of Tornado Cash have had their funds frozen inside. So once you deposit it, now you can't really withdraw, because withdrawing would mean that you call that a contract. But if you're a US user and you call that a contract, then you cannot withdraw your money onto like, fiat. Because most centralized exchanges have stopped withdrawals for accounts that have transacted Tornado Cash. Because these centralized exchanges, for example, like Coinbase, they are registered in the US, so they are bound by like OFAC regulations, not like exist as an entity and not get sued. And yeah, it's the first time that OFAC has ever sort of like gone after a cryptocurrency network, or essentially like a wallet address, or well, a smart contract address. And I mean, yeah, one of the guys like Alexei Burtsev, who was one of the original contributors to Tornado, he was arrested in the Netherlands, I think, for his role in developing Tornado. And that, caused a significant amount of outrage within the crypto community, because you're developing a tool, you don't control who gets to use the tool, right? Yeah. So yeah, I mean, I think we're pretty short on time, but yeah, we have like 2 minutes left, but essentially, brings up a couple of interesting questions, like, is privacy even achievable at this point? Because we have like the technological primitives for doing it. Like ZK can help us do it. However, if someone's going to ban it, if the government's going to ban it, no one's going to use it, then what's the point? Who should decide the amount of privacy a person gets? Should it be a government? Again, it's Tornado Cash aligned with the whole Bitcoin vision, because it's sort of like the Bitcoin vision it's very interesting take on privacy, right? Because you sort of had like pseudo anonymity, but you also have like all the transactions between addresses of the public. So in case you're doxxed, then you have essentially no privacy left. And yeah, the whole thing about like to what level can crypto exist with governments? So a few interesting questions, food for thought. It's more philosophical, but right now, it's stuff that people are working on, and it's going to dictate the future of the space in the years to come. But yeah, that is about it. I think let's go. All right. I'm going to stop recording unless there are any questions from that. And there are not. They just left. Oh, that's right. Okay, let me just end this then. Yeah, kind of